projects. In this video, we are going to explain about the project, which is automated stroke prediction using machine learning and explainable and exploratory study with a web application for early intervention. Introduction of the project. The escalating global incidence of strokes has positioned it as a prominent cause of both mortality and disability, with approximately 13 million individuals experiencing strokes annually, resulting in 5.5 million fatalities. The impact of strokes extend beyond individual health to affect families, social environment, and workplaces. This necessitates urgent attention and innovative approaches to mitigate the long-term consequences associated with the stroke. Traditional methods of predicting stroke risk are marred by their time-consuming nature and susceptibility to errors. These limitations can lead to delayed interventions, worsening patient outcomes. Recognizing the critical need for timely and accurate predictions, there is a demand for novel approaches that can swiftly identify high-risk patients and facilitate early intervention to minimize stroke-related complications. Recent advancements in machine learning algorithms offering a promising avenue for enhancing stroke risk prediction. By leveraging these machine learning algorithms, clinicians can effectively analyze various clinical risk factors to identify individuals at high risk of stroke. This not only enables early intervention but also holds the potential to reduce the overall burden of stroke-related disabilities and mortalities. The project aims to overcome the shortcomings of traditional prediction methods by harnessing the potential machine learning algorithms. Noteworthy contributions include addressing class imbalance issues, identifying crucial features through statistical tests, and proposing smart healthcare system with a web-based application. The project also introduces Shapley with explainable artificial intelligence techniques to enhance the model transparency, providing valuable insights for clinicians and contributing to the advancement of stroke care. Objective of the project. The objective is to develop automated stroke prediction algorithms for early intervention and improved stroke care, leveraging advanced machine learning techniques to enhance the efficiency and accuracy of identifying individuals at risk. The goal is to explore the effectiveness of machine learning techniques in stroke prediction with a specific focus on evaluating the model's generalization capability and prediction accuracy. This exploration aims to optimize early intervention strategies. The objective is to implement explainable techniques which are SHAP to gain insight into the decision-making process of machine learning models in the medical industry. This implementation aims to provide interpretable information for clinicians, enhancing the understanding of model predictions. The goal is to standardize complicated models and improve stroke care and treatment by utilizing global and local explainable methodologies. Standardization ensures a consistent and effective approach across diverse patient scenarios. The objective is to create trustworthy and transparent AI system that offers concise and intelligible explanations for their predictions and choices. This commitment contributes to the field of explainable artificial intelligence, fostering accountability and building trust in medical applications. To implement this project, we need hardware and software requirements. Coming to hardware requirements, we need operating system of Windows, processor of 5 and above, RAM of 8 GB and above, hard disk of 25 GB and above. Coming to software requirements, we need application of Anaconda, primary language of Python, front-end framework of Flask, back-end framework of Jupyter Notebook, database of SQLite 3, front-end technologies of HTML, CSS, JavaScript, and Bootstrap 4. To implement this project, we have designed various steps in the flow of work. So the first step is importing the packages. This module involves importing essential Python packages and libraries which are necessary for data analysis, machine learning, and web development. We have imported NumPy for numerical operations, Pandas for data manipulation, Matplotlib and Seaborn for visualization, scikit-learn for machine learning, Flask and SQLite for web development. The next step is exploring the dataset. The stroke dataset, which is containing of health-related information including gender, age, hypertension, heart disease, marital status, occupation, residence type, average glucose level, BMI, smoking status, and stroke occurrence. Each entry is uniquely identified by an ID, where patient is uniquely identified by an ID. The dataset provides valuable insights into the factors associated with a stroke, with binary indicators for hypertension, heart disease, and marital and residence status. This dataset is loaded and explored. This includes examining the structure of the dataset, checking for missing values, and gaining insights into the distribution and characteristics of the features. The next step is data processing. It involves multiple substeps. Removing missing values. Any missing values in the dataset, if present, they are addressed. This involves either removing rows or imputing missing values based on the nature of the data. Label encoding. Non-numeric data, such as categorical variables, are converted into numeric format using label encoding. This ensures that the data can be fed into machine learning models because they require numerical input. Normalization. The dataset features are normalized into a common scale, preventing certain features from dominating the model training process due to the differences in their magnitudes. Visualization using Seaborn and Matplotlib. Data visualizations are created using Seaborn and Matplotlib to better understand the relationships between different variables. This step aids in identifying patterns, trends, and potential correlations within the dataset. The next step is handling imbalanced data using SMOTE. Class imbalance in the target variable stroke is addressed by using SMOTE. SMOTE, or synthetic minority oversampling technique, is employed to address class imbalance by generating synthetic instances for the minority class in the dataset. This technique strategically creates a new data points between existing minority class instances, balancing the class distribution. By enhancing the representation of minority class, SMOTE improves the performance of machine learning models, particularly in binary class classification tasks. The next step is feature selection using select k-best. The select k-best method is employed to identify most relevant features for the model. This feature selection technique helps streamlining the model and improving its interpretability. The next step is appending selected features to X and target column to Y. The selected features are appended to input features as X and the target variable as stroke. It is designed to target column Y. This prepares the data for training machine learning model. The next step is splitting the data into train and test. The dataset is split into training set and testing set. The training set is used to train the machine learning model, while testing set is reserved for evaluating the model's performance on unseen data. The next step is building the model. In this step, various machine learning models are built and the model structure is established. This involves defining the architecture and parameters of the model. Training the model. The model is trained on the training dataset. During training, the model learns parameters and relationships between the input features and the target variable, which is stroke, using the labeled data. The next step is Flask framework with SQLite for sign-up and sign-in. Flask, a web framework, is utilized to build a web application. SQLite is employed as a database for handling user authentication, allowing users to sign up and sign in securely. User gives input as feature values. User interact with the application by providing input values for the features required for stroke prediction. This input is collected through the front end of the web application. The given input is pre-processed for prediction. The user input data undergoes same pre-processing steps as the training data. This ensures that the input is in the format compatible with the trained machine learning model. Trained model is used for prediction. The pre-processed input data is fed into the trained machine learning model. The model predicts whether the input corresponds to a stroke or not based on the patterns it learned during training. Final outcome is displayed through frontend. The model's prediction is displayed on the frontend of the web application, providing users with the outcome of the stroke prediction based on the input features. This includes indicating the likelihood of a stroke or a binary classification, which means there is stroke or no stroke. Algorithms which are used in this project are XGBoost. It is an efficient and scalable implementation of gradient boosting. It is a machine learning algorithm that uses an ensemble of decision trees to make predictions. Gradient boosting involves the sequential training of weak learners, typically decision trees, with each new tree correcting the errors of the combined model. XGBoost is known for its high predictive performance, speed, and flexibility. It is robust to overfitting and works well with the diverse datasets. The next algorithm is naive Bayes. It is a probabilistic algorithm based on Bayes' theorem with an assumption of independence between features. Despite the naive assumption, where features are considered independent, naive Bayes often performs well in practice, especially in text classification. It is computationally efficient and works well with the high-dimensional datasets. Coming to k-nearest neighbor, it is a non-parametric instance-based learning algorithm. In KNN, an object is classified based on the majority class of the k-nearest neighbors. The choice of k and the distance metric are crucial parameters. It is simple to understand, does not make strong assumptions about the underlying data distribution, and it can handle complex decision boundaries. It is used when the dataset is not necessarily linearly separable, when there is a need for flexible and adaptive model. The next algorithm is support vector machine. It is a supervised learning algorithm used for classification and regression analysis. It works by finding the hyperplane that best separates different classes in the feature space while maximizing the margin between them. SVM can handle linear and nonlinear data. SVM is effective in high-dimensional spaces and it can handle nonlinear relationships through the use of kernel functions, and it is less prone to overfitting. It is employed when there is a need for a well-defined separation between classes. Logistic regression. It is a statistical method used for binary and multi-class classification. Despite of its name, it is a classification algorithm rather than a regression one. Logistic regression models the probability of a binary outcome using a logistic function. Logistic regression is simple, interpretable, and computationally efficient. It is often used as a baseline model, and it is suitable when the relationship between features and the target variable is approximately linear. The next algorithm is random forest. It is an ensemble learning method that constructs a multitude of decision trees at training time and outputs the class that is mode of classes, which is classification of the individual trees. Random forest is robust, handles overfitting well, and it can capture complex relationships in the data. It is used when there is a need for high predictive accuracy when the dataset contains a mix of numerical and categorical features. As an extension, we have employed stacking classifier and other ensemble models combining the prediction of multiple individual models to produce a more robust and accurate final prediction. Also, as an extension, we have built class framework using testing with the authentication. We have evaluated this project using different edit metrics which are accuracy, precision, recall, and FN score. Here we have accuracy comparison graph. X-axis represents accuracy score for each algorithm, and on Y-axis we have algorithm names. Accuracy represents the proportion of correctly classified instances which are both true positives and true negatives out of total instances in the dataset. It provides an overall assessment of the model's correctness. This is the precision comparison graph. It is also known as positive predictive value. It measures the accuracy of positive predictions made by the model. It is the ratio of true positives to the sum of true positives and false positives. This is the recall comparison graph. Recall is also known as sensitivity or true positive rate. It measures the ability of the model to correctly identify positive instances out of all actual positive instances. It is the ratio of true positives to the sum of true positives and false negatives. This is the FN score comparison graph. It is the harmonic mean of precision and recall, providing a balanced measure of a model's performance. It ranges between 0 and 1, with higher values indicating a better balance between precision and recall. To execute the project, first we need to open the code folder which contains source code files. So this is the code folder of the project. This is the dataset folder on which we will be training the algorithm. This is the static folder. This folder consists of files related to CSS, JavaScript, and Bootstrap files. This is the templates folder. This folder contains all the HTML pages used in the project. It typically includes files like index.html, about.html, etc., which represent different pages of the website. This is the app.py file. This .py file contains the information related to front-end logic. It includes code written in Python that handles server-side operations such as processing user requests, interacting with the database, and generating dynamic content that to be rendered in the HTML template. This is the model file which contains algorithm information and that will be loaded into the project code during runtime. This is the notebook.ipynb file. This is a Jupyter notebook file which contains a combination of code, graphs, and outputs all in one place. It allows users to write and execute code in individual cells. This is the signup file. This is the database file used to store the user information. Now we need to copy the path of the code folder from the address bar of the file explorer. So I'm copying the path. Now we need to open the Anaconda prompt. Using the cd command followed by the space, we need to paste the copied path. Now we will paste the copied path and click on enter. This will change current directory to the code folder's path. Here we need to type the command python space app.py and click on enter. This will compile app.py file. This command will execute the Python script and perform a runtime check for any syntax errors or logical issues. After running the app.py file, Flask framework will host the application locally at the default address, which is the localhost and port unless configured differently. Here we have the localhost and here we have the port. Now we need to copy this local link provided by the framework and paste it in any web browser. So I'm copying the link. I prefer Google Chrome, so I'll paste it in that. Here we need to paste the link and then click on enter. This is the web page of the project which is displayed in the browser, and this web page is built by using the Flask framework. Here we can see a sign up link. First we need to click on it and enter all the sign up details if we are signing up new. I have already signed up and I have an account in it, so we'll directly click on sign in. Here we need to provide our credentials, which are the username and the password. So I'm giving my username and the password. Now we need to click on sign in. We have signed in successfully. These are the parameters which are need to be entered. Based on the given parameters, we will get the prediction whether stroke is detected or not. We had initially names to these parameters like age, BMI, glucose level, etc. But after processing, they are renamed as F1, F2, F3 and so on. Now we will enter all these parameters. So the F1 value is 0.7873, F2 is 0, F3 is 0, F4 is 1, F5 is 0, F6 is 1, F7 is 0.5183, F8 is 0.0753, F9 is 0.06, and now we will click on predict. I have entered all the parameters. Based on the given parameters, it has predicted as it is stroke, which means the person has a stroke. Now we will enter other parameters and see what will be predicted. Again we'll enter these parameters. So F1 is 0.121, F2 is 0, F3 is 0, F4 is also 0, and F5 is 1, F6 is 1, F7 is 0.100, F8 is 0.161, F9 is 0. Now we will click on predict. So based on the given input, it has predicted as normal, which means the person has no stroke. In this way, if we give the parameters to the system will predict whether the person has stroke or not. Now we will sign out. Conclusion of the project. Through the project, significant strides have been made in enhancing stroke prediction accuracy, leveraging state-of-the-art machine learning algorithms for early identification of high-risk individuals. The project successfully addressed class imbalance issues within the dataset, ensuring a more robust and balanced representation of stroke and non-stroke cases for improved model performance. Implementation of explainable techniques including SHAP provided invaluable insights into the decision-making process of the machine learning models, fostering better understanding and the trust among healthcare practitioners. By understanding complex models using global and local explainable methodologies, the project contributes to a more standardized and effective approach in stroke care, promoting better treatment strategies across diverse patient scenarios. The creation of trustworthy and transparent AI systems offering concise and interpretable explanations marks a significant contribution to the field of explainable artificial intelligence in the medical domain, ensuring accountable and reliable predictive models for stroke risk management.
Thank you for watching video. For more projects, please visit our website www.trueprojects.in. For updates on latest project videos, please visit True Projects YouTube channel and subscribe.